Good morning, welcome to EduSat Network. Friend, as you know, this week we have organized series of lectures on computer sciences, and we are aware that nowadays more focus on wireless network. So how the wireless network works, we will try to understand its basic fundamental concept, and we will also discuss in consequent lecture details of wireless network. So today we will start with basics and fundamentals, and for discussion on this very topic we have in the studio Dr. D.K. Lovial. He is Associate Professor in a School of Computer and System Science in Jawaharlal Nehru University, one of the premier university of the country, and he teaches there these things, wireless networks. So I think his knowledge and experience will help us to understand the wireless networks in detail. So on your behalf, I welcome him for the EduSat lecture. Welcome, sir.
Thank you, Amarenji. This is the series what we starting 4-5 lectures on wireless communication. So initially I will begin with the basics, how the wireless waves propagate and how the network works, and gradually we will move towards how the wireless LANs work and various LAN technologies used. We will be discussing on that, and subsequently we will be moving towards discussing how this 2G, 1G, 3G, 4G technology is coming up, may be more interesting to the audience because they hear most of the time of 2G and 3G in the newspapers and news channels most of the time. So in the coming week, or this week, sorry, we will be listening on to this lecture, and today we will cover the fundamentals of wireless communication, and probably we are not going in very deep of the electronics communication, and it will be from the perspective of what to be taught to the computer science students in wireless communication. That is what I will focus around, but we cannot understand wireless communication unless we understand how the waves propagate and what are the difficulties of the wireless communication, what are the various characteristics of the wireless channel, and how wireless communication has certain limitations which probably you will not find on wired communication, but what are the advantages of wireless communication which probably are not with the wired communication, and this is what we will be covering in today's lecture. So let me begin with basically with the wireless communication. What are the various physical characteristics, properties of a wireless communication? Let me define that. What makes a wireless network is it consists of, if you focus from the computer science point of view, it is a connection or interconnection of computers connected without a medium like your coaxial cable or optical cable or even fiber optical cable. So that means there is no as such a medium, physical medium existing as such in terms of a wire, but still there the communication takes place. So what should we take into account, that we probably wireless network we will also talk of the layers, how these layers work, but the most important is the physical and the data link layer, how these wireless network will differ from the wired networks. Remaining layers probably will go similarly as the other layers. So let us discuss from the physical layer itself how and that too it will mainly focus on how the signals propagate and what are the obstacles that deteriorates the signal and what are the difficulties. That is what we are going to talk about. So if you look at a wireless wave, if you first I said it is a electromagnetic radiation, how the electromagnetic signal goes from one end to other end, and that means it is a sinusoidal current running through a wire in normal sense, but here it is not a wire. So that means here the radiations are most important, right? And that means how these radiations take place. And in wired connection, if you look at, it is a conduction of current through which a signal propagates. But in case of wireless network, you cannot have a conduction that the signals will move through this. But keep one thing in mind, that before we talk of how these signals propagate, I would like to focus on, if you look at that, the moment I speak there is a speech signal, and that we call it is a continuous signal with time varying signal, continuously varying with the time. That means the moment I start talking at time t0, probably I talk till t1, and then there is an air pressure which I throw on the there is a pressure on the air and which creates a sinusoidal wave, and that is a continuous signal. And that was the initial aim of communication, that the speech must be propagated from one point to another point, and that too is initially maybe with the wire and then wireless if I put on that. then the speech is a mechanical wave. The mechanical wave means the speech signals only can propagate by the particles of the medium, and in case of a speech, the medium is air on which I am throwing the signals. That means the moment I speak, I generate air pressure, and that pressure on the air particles that makes a displacement of the particles, and the particle moves on its axis, and therefore a wave is constructed. So, if there is no medium as such air, that the speech or the sound signal, basically as a voice signal, does not travel. Either you need an iron medium or any other medium, air medium, it may be some silver, water, and because of the particles has to move. If there are no particles, the sound signal does not move. So, therefore, what I am trying to say is, and the speed of the sound wave that most of you know is 332 meters per second. So, that means it is very slow signal, but if I have to transmit this speech, therefore, I need to convert into a signal which probably travels through some other medium and faster and goes to a longer distance. Say for example, electrical signal. The moment you send an electrical signal through a wire, it travels because of the movement of the electrons, that is what you call conduction. One electron what you call vibrates, and it makes other to vibrate, and so on and so forth, and therefore, the movement of electrons also generates certain kind of thermal energy, which you probably will later call a noise. But this movement of these electrons carries the current from one point to another point. That means it is carrying a signal from one point to other point. But if you do not have wires, that means we are using again maybe vacuum, because the signals has to also travel in the vacuum, or it may be traveling on air also. So, that means we do not have some particles through which is moved. That means, so therefore, the radiations are important, which you call that because of the radiation, the electrical field is converted into magnetic field, and magnetic field change in the magnetic field generates an electric field. Therefore, the radiation takes place and the signal travels from one place to another place. That is the fundamental theory of your electromagnetic wave propagation, and that is how the wireless network will work on. Now, with this, if you look at this, what you say, how these sinusoidal waves propagate, and we say that F equal to c by lambda. C is the speed of light in vacuum, which is 3 into 10 to the power 8 meters per second, and lambda is the wavelength, and therefore you have the frequency. And this table which I have given, it says what is the range of various, or the bandwidth of various signals and the wavelength. But now why I put on this here is with two regions. Now, if you look at a wave, when this wave travels, what we need is a transmitter and a receiver, and the transmitter has to transmit the signal, and I should have a receiver which will receive this signal. Now, there are 2 points, probably I would have a diagram here, but I do not have a diagram. But what I am saying is, if you look in a communication medium, that means if I have to transmit this speech through a wireless medium, what I have to do is I need a transducer which will convert this voice signal or sound signal into a signal which can be carried by a medium. If say medium is optical, it must be converted into light signal. If the medium is called coaxial cable, therefore it has to be converted into electrical signal. So, this transducer will convert a sound signal into either an electrical signal or into an optical signal. Now, this optical signal, what you call a signal transmitting signal, which will be transmitted by a transmitting antenna or transmitter, sorry, and this signal will travel through a channel and then reach at the receiver, and this receiver will receive this signal and then is converted into a message, whatever message this signal is carrying. Now, during this transmission, when the signal travels from a transmitter to a receiver, there are various channel activities which will also intermix with the signal. That means, which will create certain kinds of hurdles or problems with this signal. Now, one, and second is, when I am transmitting this signal, the transmitter cannot straightway transmit the signal, and it has to do a lot of activities. Number one, say for example, it has to modulate the signal, and then the signal has to travel, and the channel, when it goes on the channel, there may be interference by another signal of the same frequency. Therefore, the message will have an error, or the signal will have an error, and there may be a noise. Noise is defined as an external undesired, or it may be internal as well, undesired signal which will create a problem or create error in your signal. That is how it is. That will say, for example, if a signal traveling, a wireless signal, if you look at when you listen to your transistors, if a lightning happens in the sky and the wave gets a disturbance and you are not able to listen to that radio signal. That is how, because this lightning is an undesired external signal in this case, but noise could be internal as well. The meaning hereby is when the electrons move, they also at times create thermal energy and which also creates a noise. So, there is a noise, there is an interference and so on and so forth. So, there are, and on the receiver side, the receiver has to demodulate the signal. Now, so that means in the wireless communication, there is a path loss or free space loss, or there is an attenuation of a signal. The moment I say attenuation of a signal, the meaning hereby is the signal is a composite signal. The moment I say the signal is a composite signal, what I mean to say is the signal consists of different components of frequency. It is not a single frequency on which the signal is traveling. That means the moment I speak, I am speaking on a frequency range up to 8000 hertz. So, that means there are different signals of different frequency, like some may be 4500, some is 8000, so on and so forth. And these different signals, components of different frequency will probably may attenuate with different what you call level. That means this attenuation, when I am referring to is, I am referring to maybe in a wired signal where there is a signal travels, it loses its energy, which you call attenuation, and probably which will refer to in wireless network is a path loss, that we will say free space loss. And then there is a noise, as I discussed, because noise is undesired signal, and there is a atmospheric absorption. That means the signal also gets absorbed in the water molecules in the space, and therefore, that also is very important when you transmit your signals to the space, probably at the satellite. Then there is a multipath. That means the multipath here mean, I said a signal consists of different frequency component, that is what the composite signal is, and probably it may happen that the different component of a signal may travel through different paths, and then they may reach at the destination at different times, because they are one may be traveling through a little shorter path than other, though it may be in microseconds or nanoseconds, but in communication this time, microseconds, is a good amount of time. So, therefore, even if some signal is reaching at the destination on some 1/110th of the microsecond, then there will be delay. And second is the noise is affecting the signal, and the different frequency component will be affected differently by the noise. That means when I say affected, that means the amplitude of the signal is very important, which will be affected. And then on the path there are various objects which will also create certain deviation in the path of the signal, probably which is refraction, diffraction, which we will talk a little later. Now, these are also called impairments, which really creates problem for your wireless signal. And as I said, this is what I have already talked, and the water vapors, that is oxygen, also contribute to the attenuation of a signal. That means the energy level of a signal will go down when it gets absorbed in the atmosphere. Therefore, if the energy goes down, the distance at which the signal can travel will be reduced. That means what I am saying is, because at the receiver end there is a minimum threshold level of energy which must exist in a signal. If that level of energy does not exist, then the signal will not be recognized by the receiver, or the receiver will not be able to recognize or decipher or extract the message out of the signal if the energy of a signal goes beyond a threshold limit. Therefore, if from the transmitter, a transmitter is applying a power of some amount, and as it travels it loses its power, at the receiving end the power is reducing. So, as it travels through a distance, there will be a distance at which the power will be 0, therefore, the signal cannot be recognized at all. But 0 power, we are not looking for the 0 power, we are saying there is a threshold at which it must exist, it will be much more than the 0. So, that threshold is important, and before that threshold happens, we must look for the signal. If it has to go to a longer distance, probably we have to amplify the signal. That means, we have to again increase the strength of the signal, so and so forth. And multipath I have already talked about what the multipath means, and similarly I have talked about what diffraction is. Now, let us move with the free space path loss. What does it mean? So, I talked about one thing on attenuation or in the signal. Now, there is a free space path loss. That means, what we are saying is the power of a wireless transmitter reduces with the square of the distance. That means, the power of the signal is inversely proportional to the square of the distance. Therefore, more distance it travels, more the power loss is there. That is where the problems are. Now, so therefore, long waves have less loss and short waves has more loss. What does it mean? If you look at what I am saying is PL equal to 4 pi d by lambda square. That means, the power level at the receiver end is 4 pi d is the distance and lambda is the wavelength, and so on and so forth square. So, now if you look at this power loss, P is the power loss, not the received power, the power loss. That is, if the d is more, the loss is more, if d is small, the loss is small, and lambda is the wavelength of the signal. What I said is, the longer waves or the wavelength, if the wavelength is high, the frequency is a long wavelength means the frequency is low, and short wavelength means the frequency is high, because frequency and wavelength are inversely proportional to each other. Now, therefore, when you are transmitting a signal with this wavelength and the loss is depending also on the wavelength, if you look at lambda is in the denominator when we say PL equal to 4 pi d by lambda square, where the lambda is in the denominator. So, higher the lambda, right, and if you look at the loss, lesser is the loss, because right, because this is on the denominator. So, that is very clear. So, to have longer lambda, that means to have lesser loss, we need high frequency signal, number 1. And the important point here again one has to note is, when we are transmitting a wireless signal, now on a line of sight, the most important point is what is the height of the receiving antenna. That is equally important. If you look at this, and the general theory says the height of the receiving antenna should be 1/10 should not be less than 1/10 of the lambda. If I am sending or transmitting a signal of lambda wavelength from a transmitter through a line of sight, means a straight line, the receiving antenna height should not be less than 1/10 of the lambda by 10, it should be minimum, or it should be more than that. That means, if lambda by 10, the moment I say smaller the lambda, smaller will be lambda by 10. That means, I need an antenna of smaller height. So, therefore, what do I need? So, I must reduce lambda. To reduce lambda, my f or the frequency should be higher. So, therefore, one of the reason is, why should I use a higher frequency waves for transmitting? That is what you do in modulation. When you modulate, we take a high frequency carrier wave. That means, if I have to transmit a low frequency signal, say when I am speaking to you, that means I am generating a voice signal of maximum 8000 hertz. Now, if I send this 8000 hertz, that is a low frequency signal, and the wavelength is very high, lambda is very high, therefore, the lambda by 10 will be very high, therefore, I need a very big antenna. If you look at probably a kilohertz wave, then probably you need a 3 kilohertz wave probably may need 300 kilometer long antenna. That is not possible. So, therefore, to carry this 3 or 8000 hertz wave, I must modulate it on a carrier wave of very high frequency, probably gigahertz. If I use a gigahertz frequency wave, that means the wavelength must be in some what you call is in micrometer or nanometer. If it is micrometer, nanometer, lambda, and therefore, lambda 10 will be a very small antenna you need. So, therefore, you must use a high frequency signal. Now, so what I need is, therefore, one of the reason why do you need modulation is, now you must use a high frequency signal if you have to transmit a low frequency signal. Therefore, the low frequency signal which is carrying the message must be modulated on a high frequency carrier wave. Therefore, this high frequency carrier signal wave can be transmitted on a line of sight, and needing a lower height antenna. So, that is one of, and second is probably the modulation also reduces the cost. So, the reason what I am trying to talk about is the advantage of the frequency is, as a long wavelength has less loss, but high frequency wave has, that means long wavelength means smaller frequency and shorter wavelength has more loss, that short wavelength means high frequency. Now, the one is you need a high frequency signal for keeping your antenna height low, but at the time the loss is more. So, therefore, the difficulty that if I use a high frequency signal, my power loss is more, but therefore, what you need is this signal cannot travel to a longer distance. So, what you need? Probably you need an amplifier to amplify the signal, but one has to keep at the same time in mind that if you try to increase or enhance or use amplification of a signal, the noise which is mixed with the signal will get also amplified, and then more the noise gets amplified with the signal, more difficult it becomes to differentiate between a signal and the noise. So, whereas to take a signal to a longer distance you need amplification, but at the same time this amplification results into amplification of noise, which makes it more difficult to differentiate between noise and the signal. So, that is also a trade off. So, therefore, in practice you can't carry a signal to a longer distance, but principally theoretically if you keep on putting amplifiers in between it can go to infinite length, but practically that is not possible. So, now what we said is, if you look at in the diagram, PT is the power you transmit and GT is the transmission antenna gain and GR is the antenna gain of a receiver, and therefore, the signal you apply a power it goes to a distance d and the PR is the received power, this will be low power. Now, in a line of sight propagation model, if you look at, there are two antennas put on the left side and put on the right side, and the receiving antenna height we talked about must be kept low. And the most important point in this transmission is line of sight is there are three factors, which is refraction and diffraction and refraction scattering, because I said reflection, diffraction and refraction and scattering, and reflection is also a kind of refraction. Where is a refraction, that means the instant wave deviates. If it changes the medium, it goes from one medium to another medium, it changes its angle and it deviates. Now, that is what we call refraction. When this angle of incident and angle of refraction goes beyond a critical angle, then it becomes a reflection, that means the signal gets reflected back. That is what I mean. So, these 3-4 characteristics, these impediments or these objects on the path will result into reflection, diffraction and scattering of a signal, which probably will create what you call impairments for the signal, and there is a problem. Now, if you look at two direct antennas, and on this if you look at reflection, which is a kind of refraction, I said there is a base unit from a transmitter, mobile unit or base unit, and which transmit a signal, it hits a building and that it gets reflected back to the receiving antenna, or that is antenna of a base station or mobile unit. Now, that means it was going in a path and gets reflected and change its direction, number one, and hits a boundary and then gets reflected back to other directions. That means the direction of the signal is changing. Now, there is a diffraction effect. If you look at this signal going from the BS or transmitter hits an edge of the building, and therefore, it deviates a little bit and goes to the receiving antenna. So, then when it is hitting the edge of a building or an object and then travels and deviates its path, this phenomenon is called diffraction. So, there is a reflection and there is a diffraction. Now, there is a scattering. Now, look at this. When the signal hits a small object, it scatters in multiple directions, and if you look at the base station or the antenna, receiving antenna that receives it, and the signal scatters in multiple directions. Like if the light wave hits a small particle, dust particle in the atmosphere, then the light signals scatter in multiple directions. That can be seen if you have a dust in the evening at home, you can see that in the physics. Now, there are three things. One is a wave traveling may get reflected, may get diffracted, and may get scattered. Now, it depends on the ratio of the wavelength and the size of the object. If the size of the object is very small, then smaller than the wavelength of the signal, then it gives a scattering effect. As I said, the light wave when comes, it hits a small dust particle and there is a scattering. Same happens here in case of this communication, that the signal hits a small object means the size of the object is smaller than the wavelength of the signal. Therefore, the signal gets scattered in multiple directions. And when the size of the object is almost same as the wavelength of the signal, then it gets diffracted from the edges. When the size of the object is larger than the wavelength of the signal, then you find there is a reflection effect. So, the reflection and diffraction and scattering is depending on the wavelength as well as the size of the object, which is creating obstacle on the path. And that is where and what these three characteristics do. So, that means most of the communication systems, if you look at, even if there is no line of sight at times when the signals travel, if maybe omnidirectional signal, but there may be objects on the path of a signal where the receiver antenna is. So, for receiver it may become at times line of sight. So, it may have a reflection, diffraction and scattering effect. And so, therefore, the free space propagation models are not suited for calculating attenuation, because the free space loss means we assume that there is no refraction, no diffraction, no scattering, but yes, signal gets attenuated or loses its energy because of the other factors in the space, but there is no refraction, diffraction and scattering. So, we do not use free space propagation model for where the refraction, diffraction, scattering effects occurs. Now, there are large scale effects if you look at, and that is what we are saying is, if you look at the attenuation increases with the distance, there is a power law which says P Rx equal to P Tx, the constant factor divided by D into alpha. Alpha is your what you call is a constant which varies between 2 to 4. It depends on the what you call the system property. For a wireless communication, or free space, it is taken 2, but for other kind of models it may be 3 or 4. So, it varies between 2 and 4. For free space, the alpha is 2. That is why I said that the path loss or the received signal strength is inversely proportional to the square of the distance, because we are taking alpha equal to 2 for a free space loss. But if you go on other models where there is reflection, diffraction, this alpha will increase and it go up to all. Now, that means when the signal travels, signal has random fluctuations. That means the different component of a signal will have a different attenuation and different direction. They will reach at different time, they will have different energy, and so there is a random fluctuation. And that means the fluctuation may be very quick or they may be happening very slow, and depending on that we call there is a fading effect on the signal. So, now that means the wireless signals have a fading effect due to refraction, diffraction and scattering. The fading means that the signal strength will fade. Let me quote an example here, that in a scenario that we take a WLL and at my home, and this WLL used to have a signal and it was catching the signal very well because I put an external antenna. And in June and July, August, what I find is that the signal, all of a sudden my telephone antenna at home stopped receiving signals, and that was a problem because in summer it was catching the signal very well. Now, when I try to find out the reason, what I found is that the vegetation has grown in front of the house in July, August due to rain, and that high dense vegetation has a fading effect on the signal, because this object either will reflect or diffract or deviate the signal, and therefore, the signal strength the antenna was receiving has highly reduced. Now, that means because of this vegetation in front of house, which has a fading effect, reduced the energy of a signal beyond a threshold limit. Therefore, the antenna put at the house was not able to receive the signal. So, therefore, the communication was not on, and as towards the winter the vegetation is gone, again this started working fine. So, therefore, when you are designing a wireless network, the geographic location and the vegetation around are very, very important, and if you are doing in the summer season, probably the signals may catch very well, and when the vegetation grow, the signal may deteriorate. Therefore, the designer or those who are laying these wireless network must be careful about the geography and vegetation, buildings, everything around the area where these networks are being established. Now, so these fluctuations can be modeled with different models, which we will talk a little later. But these disturbances, the interference and these introduce intersymbol interference in the multipath propagation. That means, when the signals travel through multipaths, that means the information has an error. Now, and that is what I said, the path loss, the free space is 2, urban area cellular 2.7 to 3.5, shadow urban cell 3 to 5, and building LOS 1.6 1.8, obstructed in the building 4 to 6, and obstructed in the factories 2 to 3. That is what the exponent alpha is. So, depending on the geography, depending on the structures, the path loss exponent has a different value, and therefore, the signal will fade with the different rate. That is what we are trying to say. Now, and that is these electromagnetic waves bounce off more on the conductive, that is the metal objects more, and reflected waves received along with the direct waves now will create a problem. Now, you look at this one straight line, I saw the diagram is reaching faster, but the two waves which are reflected by two objects have a delay, and because of the delay, because the signals are arriving at the different interval, then how to get a composite signal at the same time. So, you need to equalize them, right. Now, these multipath components are delayed depending on the path length. How much delay will occur? That depends on the path length. If the path length is more, the delay will have, there will be more delay, and there may be a phase shift in the frequency also. That will create intersymbol interference. Now, since we are doing modulation, probably we will either modify the amplitude of the carrier or frequency or phase. Now, since if you modify the amplitude of the carrier wave, it will be more susceptible to noise, because noise has an effect on your amplitude. So, therefore, though the information which you are carrying through this carrier wave will have more error, and but in frequency modulation the problem is you need a higher frequency spectrum, and you know frequency is a very scarce resource, that also is a problem, and then the phase also, but how many phase changes you will have per second is a more difficult issue. So, these all three modulations have their own problems. Now, so if I go little further, now what I am trying to say here is, now in a wireless medium, what you find is the wireless channels or the wireless signals are affected by the characteristic of a channel, that too is the noise, then interference, right, and that is 2, and the path loss. 3 important factors which are going to adversely affect your signal. Now, since a noise is created because of the external source, you may not have a control. But one of the important part is when you say the signal to noise ratio. That means, if the signal strength is of a given power, and what is the power of a noise signal? If you take this ratio, which is called signal power divided by noise power, and that ratio has to be high to have a better quality signal. If the ratio is smaller, then the signal quality will deteriorate. Now, there are two issues. One, for a given signal power, because noise, if I say noise is occurred due to external source, that is not under your control, and therefore, your signal power is important, and this PT by PR, sorry, PI, PN is the noise power and PT is the transmitted signal power. So, I have only control over the transmitted power which I am transmitting. Now, when I am transmitting the signal, I may increase this power. Therefore, the noise power, if I assume that the noise which is generated is a maximum level is constant, therefore, this ratio has to be high. But I cannot keep on increasing this power, because the system through which the signals are travelling and signals are being generated can also only tolerate a maximum power limit. And if you look at the first time when North Atlantic cable was laid, and it got burst due to the high voltage. So, therefore, every medium has its own characteristics to tolerate a voltage or a power. So, we cannot go beyond. So, there is always a chance, therefore, the signal to noise ratio, if the noise power increases, may go down and the signal quality go down. Now, say for example, take this example, I am delivering this lecture. So, therefore, I am a signal of certain power is travelling on the way. If somebody nearby also start talking, so this is undesired signal which also will have some power, and that is creating a noise. Now, if you take the power of my signal and divide it by the power of the signal which somebody also start talking just around me, so that ratio you have to see. Now, this ratio, what is this ratio now? If that person speaks louder than I am speaking, that means the noise power will be higher than the signal power which I am talking. Therefore, the ratio will be low, because the numerator, which is the signal power, is lower than the denominator, which is noise power. So, therefore, the ratio is low, therefore, there will be disturbance, the audience will not be able to hear what I am talking. But if you look at the other case, I am talking at this power louder and there is a certain power. If somebody just sitting around me only whispers, that means creating an undesired signal of a low power. So, therefore, the power of the noise signal is low, therefore, the ratio of signal power and noise power will be high, because I am speaking louder. Therefore, you will not find any disturbance and still you are able to listen to me. Why? Because the ratio of signal power to noise power is beyond a given threshold, and therefore, this is not creating a disturbance. So, when we talk of this noise, all noise signals probably may not be bad all the times. If their power level is low, probably they are not creating a disturbance. You can still carry your message and send your message and can be recognized. That is where you have to see the signal to noise ratio is one of the parameters to measure the quality of the signal. And this. Now, before going into other part, let me explain why do we go for modulation of signal. One reason I talked about to keep the antenna height low. The other reason I talked about is that the frequency I use is a high frequency to have a lower antenna height. The other reason is the frequency assignment is a very useful to have a modulation of a signal. Say for example, when I speak on a particular frequency and some user also may speak on the same frequency, then two signals travel on the same channel on same frequency will create interference. Now, therefore, you modulate the same 8000 hertz which I am talking on frequency x, and somebody else who is talking on the same frequency at 8000 may be modulated on frequency y. So, x is a different frequency and y is a different frequency. Now, when you simultaneously carry these two frequency x and y together, and they will not interfere with each other because they are at different frequencies. So, therefore, you are carrying the same frequency signals on different frequency carriers, and therefore, there is no intermixing or no interference, and they will be carried on the receiver side. One receiver is receiving x, other is receiving y, and x will demodulate and get the message 8000, and y will demodulate y, the other receiver will demodulate y and receive the message, and both will be able to receive the message targeted to them. So, therefore, what we are doing is we are doing frequency assignment by dividing the channels. So, the modulation is a very key factor. One is to make the message or the signal suitable for the medium. Second is to have a better efficient transmission, that is you will keep the antenna height low, and the frequency assignment that makes modulation very important factor. So, And to have interference, now the other is noise. We discussed a lot, and we discussed about modulation, and we discussed about the propagation of a signal, and we said there is a path loss, free space path loss. We said there is a multipath fading, and there is a refraction, diffraction, scattering effect, which results into fading of a signal, and therefore the signal strength keeps on deteriorating at the end, and the signal strength is very low. Now, if you look at this, probably look at your mobile communication. You have a mobile set. When the signal from a base station, which we will talk when we will talk of 1G, 2G, 3G and mobile communication a little later in the next lecture. But look at the way it happens when the signal coming from a base station comes to your mobile handset, that the transmitter from the base station has applied some power, and as the signal travels to your mobile station, it loses, have a free space loss, as well as it may have a fading effect because of the vegetation, other buildings surrounding you, that will have a fading effect. So, therefore, you have a power loss in the received signal. Now, that will determine your signal quality also, as well as how much distance this signal is traveling. Now, therefore, in certain areas, if the signal strength is very low, probably you will not be able to receive the signal, and that you will get out of coverage, or your mobile have switched off. That is the message you get. And second is, and your mobile does not show you the signals, because the signal strength, the signal transmitted by the base station or the tower has deteriorated so much up coming to your mobile station, is that it is not able to receive this signal or not able to recognize this signal. Receive this signal, therefore, it will not show any line of the power on the signal on your mobile station, and sometimes it show only one or two vertical lines. That means the signal strength is very low, and when the signal strength is very low, you may not be able to communicate, because you find that the signal strength has gone beyond a threshold. Therefore, the message, the transmission which is coming, you may not be able to receive the message or get the recognize the signal. Therefore, the communication cannot take place. One is there is no vertical line of the signal shown on a mobile. One is only one or two vertical lines are shown on your mobile. That means there is a signal strength, but it is very, very low, probably beyond a threshold or lower than a threshold. One is the signal strength has become 0 almost, coming to this because of fading as well as path loss, and therefore, there is no signal received as your base station. These are the two regions probably which shows on your mobile, which you can understand easily, that how the fading effect and how the path loss occurs in the signal. And keep one thing in mind, the kind of signal, the frequency which you use for our mobile communication is either 800 megahertz or on 5.2 gigahertz or 2.5 gigahertz, and that is what you call 2.5 gigahertz and 5.2 gigahertz, here 800 megahertz. These we call a free band, that is ISM band, industry, scientific and medical band. This is what the US Federal Commission has allotted this band for free use. That means anybody can use this frequency band without obtaining license from the government. Why it happens so is that anybody who is designing his transmitter or receiver for a wireless do not need to obtain the license, but still in India you need to have certain permissions, because in the proximity everybody uses same, then there is interference. Now, this band can be freely used, and this look at as a 2.5 gigahertz and 5.2 gigahertz. This makes the antenna height very small, because it is a high frequency signal, and therefore, lambda is very small in terms of nanometers, and therefore, the antenna of your mobile station is very low. And initially, if you remember, some of the mobile stations has some antenna shown outside your mobile station. Some of you might have seen it. The reason is, if you use 800 megahertz, therefore, the lambda is going to be little higher, little more. Therefore, the antenna height has to be little more, and that is shown outside your mobile stations in early stage. And this is what we have talked about, and tomorrow we will be talking about the details of the wireless LAN and how these wireless LANs work, and we will talk about the wireless technology to be used in this wireless communication and how it works. That means, today what we talked about, most of the characteristic of a signal or a channel, which will be determined and to be dealt at the physical layer level of a wireless communication. That wireless communication, whether you use the cellular communication, whether you use microwave communication, whether you use wireless local area network, where you use your communication for a marine and in the sea, and so forth. But the physical characteristics are important, and what kind of signals are using, you have to deal with that. And the second level we will talk about is the data link layer level, and that is where what kind of protocols to be used for the data link layer. Why I am talking about this is, one of the key point here is, in the wireless communication it is very difficult to detect the collisions, which happens in case of wired network. In a wire you can detect the collisions, here you cannot, because you cannot differentiate between whether it is a noise or whether it is something else, and the signal strength in both the directions of transmitter to receiver and receiver to transmitter cannot be same. That is where the problem is. And one of the important point which I will talk last in this is the Doppler shift, which I used here, but I did not discuss, is if your mobile station or your receiver antenna and your transmitters both are mobile, and that is, there is a difficulty. That means, if both are in motion, there is a shift in frequency. If I transmit a signal of f frequency, if the receiver, one of the, either both are stationary, that is the transmitter is fixed and the receiver is fixed. One is the transmitter is mobile, receiver is fixed, other is the receiver is mobile, transmitter is fixed. The fourth case is both are moving, the receiver is moving and the transmitter is moving. So, when both are fixed, fine. When one is fixed, one is moving, it may be fine, but when both are mobile, then there is a shift in the frequency at the receiver end. If you are sending a signal of f frequency at the receiver end, the received signal frequency will be something else, it may not be f. So, therefore, the receiver has to accommodate for the shift in the frequency. So, the receiver designed for a mobile receiver has to accommodate for how much frequency shift is taking place. That is what you call a Doppler shift. There is a shift in the frequency. So, one must take care of designing a receiver when both receiver and transmitter are considered to be mobile.
Okay. So, well friends, with this word we conclude the lecture. I thank all of you for watching the lecture, and on your behalf I thank Professor D.K. Lovial for giving such a wonderful lecture. Thank you very much.